I'll be giving a brief introduction to emulators, which is sort of, well, I mean, it's been around for a long time, but it's being more widely used nowadays since they're simple climate models that allow more robust exploration of different climate projection scenarios. And as in the title over here, you can see the added benefit is that they only take minutes. So you can look at climate model projections in minutes, which is really helpful for the general modeling society, as well as for impact assessments in looking at our climate future. So just to sort of give a broader overview of why emulators, say we are in East Africa in the month of February, as is going on right now, and we know what the temperature anomaly is relative to the pre-industrial period until this year, so 2022. How sure are we about what the climate futures will look like? Well, there's several sources of uncertainty surrounding that. One being the scenario uncertainty. So we're not sure exactly what greenhouse gas emissions are going to look like, and that in itself will affect our climate projections. On top of that, there is the general natural stochasticity in our weather system. So there is some general randomness within the system and intrinsic standard deviations that we also need to account for. And these are also accounted for by running climate models a couple of times with different sort of initial conditions. But yes, this requires also sort of different climate model runs. So we need to run several different scenarios as well as several different runs for the same scenario to also assess the inherent stochasticity in the climate system. On top of that, different models have different physical assumptions, parameterizations, and formulations. And that in itself is also a huge source of uncertainty. And as you can see, that broadens how sure we are about our climate futures for this month in this region. So that is a lot of climate model runs to do in order to assess this uncertainty. And that also comes with a lot of computational costs, which unfortunately is a bottleneck. Climate model runs take months to do. So emulators come in here as computationally inexpensive statistical tools. And all you need to do is train this sort of statistical model on the existing climate model runs. And then you can agilely explore other climate futures whilst accounting for all sources of uncertainty. So you can explore different scenarios. If you train on different models, you can also then capture that range of uncertainty due to model parameterization and physics. And there is an inherent stochastic component to emulators, which allows you to sort of infer the distributional properties in the natural climate variability. And in that way, you can then generate different climate futures whilst accounting for all sources of uncertainty. And this provides vital information for impact assessments in minutes, which is a huge improvement compared to months. Of course, it's not meant to replace the climate models, but it provides sort of surrogate results on essential climate variables so that we can assess the range of scenarios and then see which scenarios are more important to then look at with climate models. So the general emulator that I work on, which is also a product of ETH Zurich and Climate Analytics, is the Modular Earth System Model Emulator for Spatially Resolved Monthly Temperatures, otherwise called MESMA-M. And the general framework is all you need is an annual global mean temperature anomaly relative to the pre-industrial period. So here you can see we have different scenarios of annual global mean temperature anomalies. And by generating several emulations, where one emulation takes 1 minute, I can look at the regional temperature anomalies that arise from these global mean temperature trajectories, more so for a monthly level. So here you can see 1,000 emulations. You can also see that if you account for different models, there is a divergence for the high-end emission scenarios in terms of what temperature anomaly to expect in this region in this month. And you can also, of course, see how it looks across different scenarios. and it takes 1 minute. So that's also quite helpful. So just to finish off and not take too much more time, here I have a sneak preview of how exactly the emulations look. It's for the Greater Horn of Africa region, and you can see that here it's showing going from 1.22 global mean temperature anomaly to a 1.6 global mean temperature anomaly. The overall distributions can also be investigated. Here I'm showing the 5th, 50th, and 95th quantile. And in general, you can see across the months going on to a 2 global mean temperature anomaly, we capture some sort of monthly temperature pattern. And of course, you can look at how the impacts will vary. So how the temperatures change in the region according to which global mean temperature level we are at. Yeah, so that's it for now. If anyone is interested, the paper is out on MESMA-M, so the emulator that I'm presenting over here. And yeah, any questions and also feedback is welcome for sure. Thank you.